Hi, good morning, everybody, and thanks for turning up here. You get stuck with me for the next half an hour, and somebody just please shut me up if I start talking for too long, because it's been a 5-year journey with the predictive maintenance, and I've been there since the beginning of the start of this in Shell. A bit of background about myself. I've got 20-plus years in the oil and gas industry at Shell. Before that, I was in optimization. My time in computing goes back to the dark ages of punch cards and tapes. So programming and assembler was my thing. So when I look at C3's program and how many millions of lines of code they've got, it really worries me about how inefficient we've gotten these days. But it's been an interesting time. And I'll go through a bit of the journey of how we got to where we got to. A couple of things to start with. Definitions and cautionary notes, and feel free to read the small print. Suffice it to say that anything I'm going to say here doesn't reflect on Shell's performance, current or future, cannot be construed. Please don't take this to the markets and say, oh, Shell's doing a fantastic job, going to invest, and then come back and ask me why we didn't perform. This is purely around the predictive maintenance and has nothing to do with our financial performance. Where did we start with this? In 2017, and I'll go back to why we started with this. For those in the chemicals and oil and gas industry know that if you go and ask an engineer, how can I improve my maintenance? They'll tell you that they can create a fantastic white box model. It's only going to take them 3 years to build, and will need constant maintenance and could have a team of 10 people to continue to look after that. We realized that we couldn't do that across our landscape. When we talk about the number of valves and critical pieces of equipment, we're talking the orders of hundreds of thousands. And to do that would require an entire company just to look after these. Not to mention the fact that we've talked about experienced engineers, what we call the big crew change. Youngsters these days don't want to work in the oil and gas and chemical industry. They'd rather become influencers and TikTok merchants. It's much cooler than working in this industry. So we need to retain the knowledge, and we need to do it better, faster, quicker. We need to get better about what we do. And at the same time in Shell, safety is our top priority. So no harm to humans, no harm to the environment, and ensure that we are keeping things going well. So we said, how can we do this? And we started off with a grad project with Delft University, looking at how we could apply statistic modeling to try to determine if we could predict equipment failure. It was fairly successful. And it was applied across a number of known failure cases in the past. We looked at compressor for one of the compressors on the offshore facilities in the North Sea, and the same applied there. So we said, okay, there's a basis for this. But that in itself was just the starting point. We said, okay, how can we grow this? And somebody came along and said, talking of data and data quality, somebody said, well, we've got 2 million valves in Shell. How are we going to go from 2 valves to 2 million valves and do it in the next 6 months? That was a challenge I was given. I said, that can't be right. We did some checks on the numbers. It turns out we've got around 5 million PI tags. So for those of you who use OSIsoft or Aviva, we've got 5 million of those across all our assets. Currently today, we ingest and we generate data at the rate of around 15 million data points a second. C3 has had the arduous task in the fights with me about having to ingest this data at rapid speed and process it. So how do we get to that growth? So we started off an accelerator on that, and we got to 32 valves after a period of time. But we missed a whole lot of the basis and the underlying pieces to how we would manage orchestration, how we're going to manage the data normalization, how do we deal with data quality, how do we deal with missing data, how do we deal with not building a bespoke solution that is only applicable to one asset. Adi got a knock on the door, I think, when we were working in Australia on another project. And we gave them a challenge. We said, take these, replicate this, and show us you can do this for 500,000 models. I think he scratched his head and said, what? So it was a good challenge. We went through that with analysis. Yes, they proved they could do it. Yes, we proved we could do it as well. And we started working that. So at the end of 2018, we said, okay, we'll work with C3 This gives us the best opportunity to take advantage of moving forward rapidly from where we are today to scale this up to the order of tens of thousands of models. By the end of 2019, we got to a massive 100 models live. So it wasn't all smooth sailing. But at the same time, we took our knowledge of the C3 platform, of building applications on it. C3 at that stage, Adi, correct me if I'm wrong, 250 employees max, I think it was. And we had nobody with any C3 experience in Shell. So we built up a dedicated team. We learned on developing the application. We needed a cross-functional team. This was not a technology or an IT-led project at all. It was baked into the business process. So there was a lot of stakeholder engagement around the change management of how to improve the process, bring the engineers along with the journey, the control room operators who can be grumpy at the best of times, ensure that they are on board with this, because it's not a technology that we're going to put in to say, thanks very much, but we don't need you anymore. We couldn't afford a risk of a failure at a plant that was catastrophic. There is no way we would put people in harm's way. So we had to ensure that what we were doing was, let's say, well thought out and well maintained. In 2020, we started focusing on replication. And we scaled back from our original intent of trying to cover the globe from the west coast of Australia to the west coast of the US all at the same time. For those who've been around long enough, might remember an Accenture advert about building airplanes in the sky. Yeah, it doesn't work well. We scaled back, we focused on one asset, we got it right on one asset, we brought people along with that. We focused on identifying small areas of failures with a mantra of sort of find small, fix small. There's no point in trying to look for the tens of $1 million as your first example and go back to senior management for more funding and say we found these huge problems. Look at the small ones, celebrate those successes and move forward on it. We expanded out in 2020 where we'd proven that we could run this at scale. I think, Adi, you mentioned as well, we're at some 28 assets now, some 50-odd applications running across the space, covering numerous areas. In 2021, we got together with C3, Microsoft and Baker Hughes and formed this OAI initiative and said, the days of old where we used to build solutions and keep them under lock and key in Shell and said this is proprietary technology, we are working more collaboratively with the marketplace. We realize there's benefits in working together. We do that in the subsurface world under things like the OSDU agreements. And also get inputs of other people as to what the problems that they're facing. So that was the intent of that. We expanded the compressor module out to what we cover as critical equipment. So we now cover turbines, compressors, and pumps, both reciprocating compressors and centrifugal compressors. And we started taking a centralized approach. So experienced engineers are difficult to come by. They are retiring, they're leaving, they're going places. Thankfully and hopefully generative AI is coming along. I don't know, we'll see what that brings. But we set up centers in India, which we call our technical asset operations. And they do most of the triage and monitoring for us worldwide. So they're the first port of call. An alert comes in, they pick it up, they assess it, they pass it back to the plant and the asset where it's needed. If there's something to be acted upon, that's then put into the work order and so the work carries on. We extended out our control valve application to cover other pieces of equipment as well. So taking the basis of what we built out for the reliability application there, we found that we could apply the same logic and the same algorithms to other equipment. Why was that of benefit? It meant we didn't come up with a new solution. We didn't go off and build another solution. We didn't have to evaluate it. We already had the basis in place. All the data and the applications were there. Some minor changes to it and some immediate benefits. Back in 2022, 2021, I think these were all the challenging years when COVID was around as well. We also we're fortunate. We got awarded a Manufacturing Leadership Award for use of AI in the industrial space. Again, this is quite an accolade, given that this was the sort of first time that AI had been considered in this, where traditionally, if it wasn't a fine engineering calculation based on thermodynamic libraries, it wasn't considered. But people started realizing that things are changing, and we've got new things on the way. In 2023, so this past year, what we've done so far is we've tripled services with value. So it's all fine generating an alert, but if there's no action coming from that, then is it a genuine alert, or is it something that actually was worth seeing in the first place? Where we've got services with value, that means that somebody's physically gone out and done something to a piece of equipment which has added value into the system. So we're increasing our number of services, at the same time reducing the number of false alerts. We did a deal with C3 where we've transferred our intellectual property for the centrifugal or the critical equipment application and the application for control valves, so they'll incorporate that in there. Part of the reason that we took our approach, as I mentioned, was how do we scale up very quickly? And if I have to build a model from the ground up by going through my data, which is inaccurate, unstructured, irregular at best, and I need a subject matter expert who's got detailed knowledge of the plant and all the P&IDs, I'm not going to get to the numbers that we needed to get to. So we took a different approach with the control valves, the way we do it with correlations and creating the models and automated training and bulk training. I think to date we've trained about 1.5 million or 1.2 million models. And we have over 20,000 currently running on a day-to-day basis generating predictions. And that number's continuing to grow, as well in other areas. The solution is now business managed. It's been handed over. It is in full-blown production, and we continue to use it and grow the capabilities of it. What did we learn along the way? First off, identify the problem we're solving. There's no point in saying, I've got this wonderful AI tool. What can I do with it? Let me think of something weird and wonderful to solve. Take real-world problems. We said we had trips were our biggest problem. The two biggest areas were compressors and valves. They were costing us money for deferred production because a barrel produced today is worth more than a barrel produced tomorrow. And in the downstream side of the world, if we shut down a plant, it's in the order of millions or tens of millions a day. We knew those were issues. We knew we had to solve them. We knew we could get value from them. So we focused on that. Product development and replication are different. Yeah, developing the solution with an asset, with the subject matter experts, is not the same as replicating it to different assets. Our assets have grown through acquisition organically. We've got a mixture of brownfield assets, greenfield assets. Assets that have been around for 50 plus 60 years with all various levels of quality of data. The tags are named with naming conventions, no naming conventions. In English, Dutch, German, Cyrillic, you name it, we've got a combination of them all. So we need to be able to take what is in an asset and actually use that data. Asset hierarchies are not the same all over the place as well. They've changed. We've had to work a lot on the data. So one of the first things we do is a data quality assessment as well before we go full scale. Always start fixing or normalizing the data so it's usable. Build on existing products where possible. Yeah, we started the journey in 2017, and we didn't change a lot from there, other than use C3 as the platform to do it. We've taken the control valve application and applied it to other instrumentation in the refining and the upstream business. We didn't rebuild. We didn't change the application, the basis of it. We kept the original state of it. Replicate only when the product is ready. Yeah, don't build an airplane in the sky. They tend to fall out of the sky. So you need to have the base minimum functionality. Waterfall methodology is all fantastic and great until it doesn't work. That's the quickest way to lose your stakeholders and your funding. Embed the product into a work process. This is not a technology-driven product. It is not an IT-led product, and it is not an AI-led product. This is a real business problem that needs a real solution. And if it's not in part of the process, it's an afterthought, and it's not accepted. So change management is absolutely critical to this. Scaling required internal and external partnerships. Yeah, external partnership, C3. This is where we partnered with them. We needed them to get there. Could we have gone a different route? Yeah, we could have used Amazon, AWS, Google Cloud. We could have gone Azure ML. At the time, we're going back 5 years, they were all at different levels of maturity. So our best option was the option that we chose. Our outcomes, what did we end up with? We ended up with an enterprise platform. Does that mean that C3 is the only platform for AI we use in Shell? No, absolutely not. We have data scientists working day to day using Python, Jupyter notebooks, all sorts. We're not going to stop that. That will continue on. If we look at the federated sort of community data scientists we've got across Shell, in the order of some 4,000 people. That could be anybody who's working as an engineer at the plant, who's got some data sciences, who wants to try something out, who does a sort of build your own application on site. Those we'll look at, and some of those then mature up the path and become an enterprise solution. Some problems are unique to a given asset, and obviously we won't invest the time and effort in building an enterprise solution for that. AI Competency Center. We've grown the Competency Center so from 0 staff and people in the space of building enterprise AI solutions. We built that capability to over 50-odd people directly involved in delivering the solution, to some 200 people if I take the extended people around the change management engagement, the people in the assets, the people in the technical asset operations that use the tool, that provide the feedback to us as well. And that's continued to grow. Global deployment and adoption. Where we look at it, and I think also when I joined Shell some 20 years ago, I remember working optimization and got told the first thing when we're dealing with some supply optimization that somebody said, oh no, you don't understand. The business in Australia that we have is entirely different to the business in Europe. It's not. We produce oil, we produce end product, and we ship it to a customer. Yeah, fundamentally, it's the same process. So where we can build out them, and we built out one single solution. There is no customization. Each plant hasn't got its own version of this solution. There is one centrally hosted application in Europe that is used globally. The models are all different, but it's the same solution. Increased availability. Increased availability of our assets. Obviously, this has all led to equipment uptime, allowed us to continue operating our plants better. Some of the things like our remaining useful life in the products that we've got baked in allow us to assess the degradation or the rate of wear on parts of the equipment. We know that we can extend the life of that out to a planned maintenance activity or a scheduled maintenance activity. So that allows us to change the process to ensure that we can keep running, rather than have an immediate failure problem where we have to shut the plant down, do a break fix, and carry on again. Ongoing value realization. Yeah, we have to continue to realize value. It's a very difficult one, and I'm sure you've got the same problem. When you want money for investment, you've got to measure the value you're getting from it. How do I measure the value of an asset that's got no failures? Uptime. So it's a balance, though, because then my value is 0, but my uptime is 100%. If I get to 100% uptime, I'm doing fantastically. But people still want a dollar value attached to it. So we do measure that with the assets. It's not a number that we centrally generate and dream up. It's not an NPV calculation. It's based on real outage activity that we would have incurred and maintenance work that would have had to be carried out. It's supported by the assets, by the engineers themselves, and we report it accordingly. I'm not going to read through the text on this one, but these are just a couple of examples of some failure cases we had. One was around a control valve. There were some deviations on it. If we'd had that, we would have had a deferment, and I can't mention the number of barrels equivalent. but it was a fairly significant outage that could have occurred. So these things were an early finding that was put in there. This piece of equipment wasn't scheduled to be maintained during a turnaround activity, but it was subsequently added to the list, and the defect was addressed, and then startup ensued, and so normal operations carried on. Critical equipment, yeah, pumps, compressors, wonderful things, require lubrication, have bearings, bearings tend to fail, gas seals fail, all these kind of things. When those do, they're either catastrophic, it's fairly cheap to replace a bearing, it's very expensive to replace your entire compressor, particularly if it's a big one. And not to mention, when we were discussing it a little bit earlier, before this all started, we did have an incident somewhere where, through fortune, we happened to have a spare compressor of a very large size at a given facility. If not, there would have been an 18-month lead time for a replacement. And that's shut in production for 18 months. So you can do the maths on a large asset, what that would equate to. So these things are what we focus on. Early detection of anomalies reduces our unscheduled deferment, unplanned downtime. That's a given. That's all the plants want to do. In the good old days, a refinery manager was tasked with run the refinery at 100%, produce as much product, spit it out the other end. I don't care if you need avgas or mogas, just produce. We've changed that around in the business these days. It's more a demand-driven supply chain. We know we can make changes to the product production. We can improve our avgas or mogas depending on the time of the year, depending on travel patterns, depending on needs. But one thing does remain, we need to keep the plant running and available. So that's where we need to run. Do we reduce our maintenance costs? Timely intervention, yeah, catastrophic compressor failure is far more expensive than replacing a bearing. I won't get into contracts with General Electric or Baker Hughes, but quite often, so if anybody's used Predix in the past as an example, or got contracts with some of the equipment manufacturers, if you say we want a 99.9% uptime, they will come in on a Monday and say, by the way, we need to shut down compressor 235A because it's going to fail. And you say, well, no, we're in a critical production stage. And they say, well, no, to keep your uptime, we have to shut it down. We don't care about your production. We're in control of our own destiny now. We recommend when to shut down. We recommend when the maintenance activity carries on. Use AI to find small and fix small. Yeah. Fix a problem when it's small before it becomes big, because when it's a big problem, AI is too late. Where we are in the product space at the moment, and this has been a journey, I would say these are the products we've got live and in production. Coupled with this are numerous proof of concepts in various areas, covering the upstream, downstream integrated gas, and the renewable space as well. So we're continually evaluating where there are additional use cases to apply AI and AR solutions. So real-time process optimizer is used in our LNG plant, and Lina touched on that a bit around process optimization and incorporating that with predictive maintenance. If you can improve your process by the order of 0.5%, 1% in terms of dollar revenue values, it's considerable. Corrosion and risk modeling and analytics, a product we call Karma. Corrosion is a problem. We deal with products that have a lot of water in them, have a lot of sulfur in them, have a lot of corrosive materials in them, H2S gases. And some of the plants are all covered with cladding. And to discover corrosion under cladding is very difficult, near impossible to see. So we use various methodologies as well with an AR tool, also built on C3, to assist us in that space. Autonomous integrity recognition is a machine vision use case that we use for evaluating the plants when we're doing inspections. So we'll go off and take a whole lot of drone footage. We'll send inspectors around. They'll take photographs around the place. We have a number of use cases we can apply that against, and we measure against that as to previous known issues. So we've identified a number of areas where we've picked up anomalies with that, but also reduced the inspection time and turnaround, which is a sort of cost saving. Operator rounds by exception. This is a robot we have running in a number of plants, going around doing inspections. So this is part of the HSSE side of life, taking people out of harm's way. We can take a physical person out who has to go and walk around in miserable snowy conditions, blizzard conditions, whatever it might be, or extreme heat conditions. And the robot can go and do the work to evaluate, read gauges, check meters, ensure there's no leaks, listen for sounds, and respond accordingly with feedback. ESG is an area that obviously is keen on everybody's mind as well. This is something we're looking at and evaluating right now. And Shell Remote Sense is a product we've built which is equivalent to a lube analytics product, but using AI to determine properties and replacement of lubricants. How am I doing for time? Any questions?
One problem I see with predictive maintenance is that in view of change management, that there are no kind of heroes anymore. I mean, if you change your things before they fail, there's no one who can stand out and say he's the hero. He managed the situation, and it's if everything is running smooth, there's no how would you say? There's always the question: why do we need preventive maintenance or predictive maintenance if there's nothing failing? You know.
I 100% agree with that one. There's a couple of things in this one, and it's if you go to an asset as well and you say, well, we're putting this fantastic solution for your predictive maintenance, they go, yeah, but we've got 20 other programs we're running at the plant with real asset engineers day to day optimizing and making things better. So we already knew these problems anyway. If we reduce that, the next problem that comes around is the asset's budget for their maintenance activities gets cut. And they don't like that either. Change management is absolutely key to this. You have to bring the people on the journey. And so what we do is, again, it's around celebrate the successes, find small, fix small. And it isn't about, yeah, we found a problem that was worth tens of millions of dollars. It's a problem that we said we avoided $100,000 in cost, or a $20,000 replacement activity. And keep celebrating the small activities. Reward the teams. Highlight the members who worked on the problem, who saw the issues. And it's continuous work in that space. And it's not going to go away. The minute you stop doing it, the interest goes away again, and you're back to where it is. The quickest way to see if it is working is to stop doing it and look at your reliability. The problem is nobody wants to take that risk. We're not going to take that risk. If it is applying, is delivering the benefits, we're going to keep doing it. But it is hard to justify when you're spending money and you've got 100% uptime.
Richard, thank you for sharing those learnings. That was very interesting.
In terms of bringing this to the business, do you use a push or a pull model, or is it a bit of a combination of both?
A combination of both. So it started off as a pull. So somebody in the asset space turned around and said, by the year X, we're going to have, our goal is 0 trips. Yeah, very ambitious goal, because we know that's near on impossible. Even on a brand new greenfield site built from scratch, you're going to have problems and outages. So it started with a pull saying, that's our big, hairy, ambitious goal. 0 trips, we know that that's going to lead to X dollars in value around reduced deferment and increased production. And then we said, okay, let's look at that and evaluate how we can address that. The 2 biggest contributors were control valves and compressors. We said, okay, we'll build a solution out for that and prove that we can actually do something. The next step was how do you scale that without using discrete first principles-based engineering models or white box models. And that was the way we said, okay, we can scale these faster than you can build, a single model for one piece of equipment at a given asset. We can do it for multiple pieces of equipment for the entire asset. So it's a combination of both, absolutely.
Okay, well...
We've got one more over here.
So, do you see like sense in applying those concepts in an industry where you have smaller assets and batch-wise running assets? I mean, the thing is, you have your really big compressors. They cost a fortune to keep a spare compressor. So you can really stuff them with sensors and things like that. But where I come from, we have the problem we don't run continuously, so that we always have ramp up, ramp down, or maybe just do other products, so multi-product facilities. And our assets are much smaller. So when we talk about pumps, they are smaller pumps. So we would need more, way more sensors, and they are more easy to replace, less cost of keeping spares. What would you advise on doing with AI and predictive maintenance?
I don't think there's a right answer on that one, my opinion. And in fact, actually, another national oil company, the way they run their equipment is they run it as hard as they can for as long as they can, as fast as they can, until it breaks. So they operate on entirely different conditions. To them, they don't really need to predict things. What they need to know is they're just going to run it flat out. We do have small pumps and small compressors as well. There's also entirely different parts to our plants. The intention is to look at this and say, where we have critical equipment that could lead to let's say, the entire plant being shut down, that is something we would like to monitor. And what is critical is quite often difficult to see. So back to the data and data quality. I can go through and I can look at criticality in my SAP system on our on the plant management systems. And there are pieces of equipment there that people say that's absolute nonsense. That isn't a critical piece of equipment. An effluent valve, for example, that's a relief valve. Somebody says, well, that's just not critical at all. If it goes wrong, and we suddenly dump a couple of tons or 100 tons of hydrocarbons into the Rhine River, it's a very critical valve. It's not critical, but it is critical. So you have to make those decisions as to what applies. And you can run smaller AI models that, give you the same results, or it doesn't have to be a massively scaled solution. What we're doing as well, we've got a lot of older assets. If we took the Rhineland refinery or Pernis refinery, we're adding instrumentation to it and sensors to it. Lower WAN sensors, wireless sensors are becoming far, far cheaper. We don't have to worry about APEX or ATEX approvals for these equipment. They're already done. In the past, to add a flow meter to a pipe in a refinery was probably in the order of 20,000, 30,000 plus, assuming all the rest of the infrastructure was there for it. Today, you can do those, for the order of 1,000. So it is changing. We're getting a lot more data. There is more and more data becoming available, which leads to better models, better predictions, better ability to react. New pumps, new compressors, they're coming already pre-sensored with all the availability of that. So it is changing and will continue to.
Question, did you also observe some examples where you maybe had to increase the budgets?
Where we had to increase the budgets?
Yes, to realize the total performance.
I don't believe so. So we've stayed within, I think what's happened in some of the assets, we've actually reduced the spend on maintenance activities. Where we've taken out certain activities, such as planned and scheduled, every 6 months you're going to go and work over a piece of the plant. We've realized we don't need to do that. So that activity can be taken, and the money that was being spent there could actually be utilized elsewhere. Pre this, even, I can say, this is something we've been looking at for quite a while. So an ESD device at an offshore facility, an emergency stop device. We had I think historically, years back, we used to say every 3 months or every 6 months, you had to do a full test of that to ensure that, when that kicked off, the entire facility shut down. That meant every 3 months, every 6 months, you were stopping an entire offshore facility. You were shutting it down. You had to do the startup all over again. There was all that lost production all the time and the risk. We then started collecting data on that and said, well, instead of doing it every 3 months or 6 months, we can actually, the historic failure of these things has been so long that we can actually do it every 2 years or every 4 years. There's no need to do this every 3 or 6 months. And you can go back to the sort of the governing bodies around us and saying, this is the proof that we've got to say that we don't need to do this. So we're not running a risk of a catastrophic failure. We can actually prove with data points that these things are unnecessary. It's other ways to look at it is saying, we focus on an area of the plant. We still got our turnarounds and workover activities for the plants. We process corrosive products. We know that you have to replace certain things. It's going to happen. But what we can do is, while we've got a shutdown in an area, we know that a piece of equipment that may have an issue, we can bring that in for a service activity that wasn't planned. And that saves us money because after startup 2 months down the line, we don't have to go shut it down and start up again.